Good evening, everyone. First and foremost, if the voice and video both are fine, please let me know. All good? All right. Wonderful. Hmm. So let's begin with our session. So today, the first part of our discussion will be about nuclear reactors, India's nuclear program, and the applications of nuclear technology. So these are the things that we are going to start with. So probably the first half of the class up till you can say almost the break will be doing this. And then the next part of our class, we will be starting with our second chapter, that is space technology. Now, so let's start with the first part, that is about nuclear reactors. Now, until now, what we have discussed is about, you can say, the theory or the science of nuclear energy. What is radioactivity? What is nuclear fission? What is nuclear fusion? How did we come to know about something called as nuclear energy? So there are different concepts of science related to nuclear energy is what we have discussed until now. Now, this part that we are starting now is, you can say, more related to the technology of nuclear energy. The technologies involved, how do we get that energy, where are we utilizing it, how are we utilizing it, what is India doing? So these are the things that we're going to discuss in this part of our discussion that we are beginning now. So to start with, we are talking about nuclear reactors. Now, these nuclear reactors, these are nuclear fission based reactors, as we discussed yesterday as well, that there is nothing called as fusion reactors right now. These are just experiments that we are doing right now. Whether it is the Japanese reactor that is now functional, or whether it is the ITER which we are planning for 2035, or whether the experiments being conducted in the US. So wherever we have any fusion based reactors, these are experimental in nature. But when it comes to the nuclear reactors that we are going to discuss here, these are fission based reactors, and nuclear fission is what we use for generating electricity via nuclear energy. So, nuclear reactor. So, first, let's try to understand the basics related to nuclear reactors and the various different parts that any given nuclear reactor has. Now, at the center is something called as the core. The core of the reactor is where the reaction takes place. Your uranium, the bombardment of uranium will happen here. So there will be uranium based fuel rods that we would have, and these fuel rods will be used in case of nuclear reactors. So the core is where all the reaction occurs. So this is where the reaction occurs. This is where nuclear fission occurs, and hence this is how we get the energy from. Apart from that, you see another part here called as the control rods. Now, the role of control rods is to control what? Control the number of neutrons. Because what we have understood is that we need to control the chain reaction, correct? To control the chain reaction, one of the aspects of controlling the chain reaction is to control the number of neutrons that is participating in a reaction. So that's why to control that number, we have control rods. What does a control rod do? Control rod will be inserted inside the core whenever the number of neutrons is rising. If it is above the level that we need, then in that case, the control rods will be inserted inside the core. And this is where it will absorb all the extra neutrons, and then it will be taken out whenever our requirements are done. So control rods basically will control the number of neutrons. All right, they will control the number of neutrons by absorbing any extra neutron that is there at the core. So they do what? They control the number of neutrons. Control the number of neutrons. And then apart from that, there is another part which is there at the core itself, which is mixed, you can say, in a manner in the core, and that part is called as the moderator. Now, moderator also is one of the ways in which we try to control the reaction, but this time not by absorbing extra neutrons or controlling the number of neutrons, but rather by controlling the speed of neutrons. All right, so they would do what? They would control the speed of neutrons. All right, we would control the speed of neutrons with the help of a moderator. So we have the core, we have the control rods, we have the moderator. Apart from that, you see that there is a reflector. So reflector is, you can say, like a wall. Right, this is like a wall of the reactor, and then after that we have a coolant. So wall basically will be a thick wall made of either steel or concrete. Thick wall, at least 15 centimeter thick wall of concrete or steel, so that ensure that we are able to ensure that none of the neutrons get out of the reactor, or none of the energy particles like gamma radiations or beta radiations or alpha radiations or neutrons or high energy particles, photons, they are not able to get out of the reaction core or at the out of the reactor core, because they otherwise can be very harmful, because these are very high energy particles. All right, so because they are high energy particles, them getting out of the reactor is going to be very dangerous for the human and environmental health. So that's why this wall will protect that from happening. Then we have a coolant. Now the role of a coolant is basically to carry the heat of the reactor to the secondary side, to the turbine. So the coolant basically carries heat, or let's say energy, carries energy from core to turbine. All right, so from the core to the turbine they would carry the energy. So this is basically the role of a coolant. So these are some of the important parts of any given nuclear reactor. All right, these are the important parts of any given reactor. The secondary side of the nuclear reactor that you see on the other hand, this is common for any kind of energy, or whether it is thermal electricity power plant, or whether it is a geothermal electricity power plant or nuclear energy power plant. You'll see that the second part is always pretty common, that there will be steam that will go to the turbine, it leads to the rotation of the turbine, and hence it leads to generation of electricity from here on. So this is basically how we deal with the second part. So just to revise everything that we discussed, so there will be a reactor vessel. So reactor vessel will hold the other reactor parts all together, and then we have the core contains the nuclear fuel. So that's why this is the part of the reactor where fission occurs. All right, so this is where the fission occurs. And then after that we have the control rods, which are largely metal rods, contain elements such as boron or cadmium, and these absorb free neutrons. That's why they would help in controlling a chain reaction. Correct, they would control the chain reaction by absorbing all the extra neutrons from the reactor. So they would be inserted into the core or withdrawn to slow down or speed up a chain reaction. Apart from that, we discussed about moderators. So moderator is a substance such as water or carbon that slows down neutrons which pass through it. So what do? They would slow down the neutrons. Fast moving neutrons are less efficient. Let's say this. They do not produce as much energy as slower moving neutrons do in most of the common reactors. So that is the reason why we would want to slow down the neutrons, for which we use moderators. And then after that we have the coolants. So coolant again can be water, carbon dioxide, etc., that conducts heat well, at the same time does not easily absorb free neutrons, and that's why it carries the heat from the chain reaction to the turbine. Now, one thing that has been written here is that it does not easily absorb free neutrons. Now, understand the meaning of this phrase. We have control rods, right? And the role of control rods is to absorb any extra neutron that might be there in the reactor. Correct? Now, in this particular scenario, suppose the coolant, which is supposed to carry the heat from the reactor to the turbine, let's say if it is also made of a substance which although conducts heat well, but at the same time also absorbs neutrons, then what happens? Then you will be left with fewer number of neutrons than what you need in this reactor. Correct? So that's why you also need to ensure that whatever the coolant is not withdrawing or absorbing extra neutrons from this reactor. So that's why this is also, which is something which is very very essential in any given reactor. Now, looking at the different types of nuclear reactors, what we see is that there are various different designs that are used all across the world. But we are not really concerned about a lot of these reactors. What we are concerned about are the reactors that are being used in India by India. So we'll look at some certain designs which are very crucial part of India's nuclear power program. So first is a pressurized heavy water reactor. Now, in a pressurized heavy water reactor, there are two terms that you see: pressurized, heavy water. So, we'll try to understand why pressurized, what is heavy water, why are we using heavy water. So, that will make it clear why exactly this design is so popular. Now, why am I saying that this is popular? Because if you look at all the reactors that we have, out of the 2021 odd reactors that India has, 18 of them, they are just pressurized heavy water reactors. So that tells you that this is the most common reactor design. And again, not only in India, but worldwide. You'll find that world across, this is the reactor design which is most commonly used all across the world. So the fuel that we use here is enriched uranium, that is uranium 235, as we discussed yesterday. So uranium 235 is being used. Moderator and coolant that we use here is heavy water. Now, when we say heavy water, understand what do we mean by heavy water. All right. So, if you look at this reactor design, and no need to be afraid of these kind of diagrams that we see here. If you look at the essential components, they are similar to the block diagram that we had just seen. So, if you see this, you have the same control rods, you have same fuel elements. So, this basically forms the core. This basically becomes the core of the reactor. And then again, there are pressure tubes because these are pressurized heavy water reactors. And then you have a steam generator which generates steam. Steam again is carried to the same turbine. All right. The steam is carried to the same turbine. From the turbine, this goes to a condenser. All right. It goes to a condenser, and from the condenser, it comes back with the help of a pump. So in this manner, we see that there is this cycle that is being maintained in this particular reactor. Now there are two things. It is a pressurized heavy water reactor. Why pressurized? And what is the role of heavy water? So first, why pressurized? Now when I say pressurized, the meaning of pressurized is what? That this is running at high pressure, correct? It's running at high pressure. That's why the term pressurized is being used. Now, when we say that it is running at high pressure, understand why high pressure. What is the significance of high pressure? Now, this is something that I also told you when we were discussing geothermal energy. When we were discussing geothermal energy, and especially when we were discussing flash steam power plants. Do you remember what I discussed about water being at high pressure? What happens when water is at high pressure? Anyone who remembers, can you tell me quickly? Otherwise, anyway, I will tell you, don't worry. But anyone who remembers, I want to see who have revised well and remember. What happens when we have water at high pressure? Akshay, correct answer. Anurag, correct answer. Srinivasa, correct answer. Faris, correct answer. Shahid, correct answer. Neil, correct answer. Ravi, correct answer. Wonderful. I got many correct answers. So pressurized. So what we discuss? We discussed that when you have water at high pressure, it does not uh, change into steam at its normal boiling point. Normally, what happens? You keep a bowl of water, or maybe you start heating water, and what do you see? That as soon as it reaches 100 degrees Celsius, it starts to convert into steam. Correct? But when you have higher pressure than usual, higher than normal atmospheric pressure, then in that case, water does not start boiling at 100 degrees Celsius, but it might start boiling at a higher temperature. All right. So what happens is that when you are maintaining very high pressure, even if this water is at 120 degrees Celsius, 150 degrees Celsius, yet it remains in its liquid state. It doesn't convert into its gaseous state. And in this scenario, we see that it is able to absorb energy more efficiently. So that is the reason why this is pressurized heavy water reactor. So water at high pressure, water at high pressure is capable of carrying more heat without converting into steam, even at temperatures above 100 degree Celsius. Right? So this is basically what we see, and that's why pressurized. So we are increasing the efficiency or the heat carrying capacity of water by doing that. Now the second question. The second question is, why heavy water? Now first question that I have for you is, what is heavy water? What do we mean by heavy water? What do we mean by heavy water? D2O. D2O meaning that this is water made of deuterium, right? So this is deuterium based water. In short, D2O. So instead of H2O, we write D2O. So deuterium base meaning what? If you remember, we discussed that there are three isotopes of hydrogen: the normal hydrogen, deuterium, and tritium. So deuterium is the one that has one proton and one neutron, correct? So deuterium is, that's why it is called as heavy water, because it has one extra neutron. So that's why it is heavier than normal water that we use on a daily basis. Now again, why heavy water? What is the advantage that we get out of heavy water? Now, normal water has one proton and one electron. Normal hydrogen, sorry. Heavy deuterium has one proton, one electron, and one neutron. So there is one extra neutron. Now, because there is one extra neutron, its capacity to absorb extra neutrons decreases. Correct? So when it is inside the core, it will not absorb neutrons easily, right? It will not absorb neutrons easily because it already has an extra neutron. So that's why compared to that, light water or normal water still has some capacity to absorb neutrons. So that's why when we are looking at a scenario where we don't want absorption of neutron, in this particular scenario, it's better to have deuterium based water as compared to normal water. So this is precisely the reason why do we use heavy water. All right. So heavy water has an extra neutron compared to normal or light water. So it has lesser capacity to absorb extra neutrons from the core. All right. So this is basically what happens. So that is why heavy water. Now there is another question that you might ask: why not tritium? Why not use tritium water instead of deuterium water? We don't use tritium water mainly because tritium is radioactive. Tritium is radioactive and tritium is very highly unstable. So that's why it's very difficult to work with tritium water. Deuterium water does not have that problem. D2O does not have that water. Heavy water, meaning, doesn't have that problem. But tritium water might have that problem because tritium is radioactive. So we don't use tritium water as tritium be radioactive is not stable enough to be used as a coolant or moderator. All right. So this is basically what we see. This is basically what we see. And overall, when it comes to the use here, we see that heavy water has that sweet spot where neither it would absorb anything nor it is unstable. So that's why it is preferred in these cases. So pressurized heavy water reactors, that's why these are the most common design, not only in India, across the world. Then the second reactor that we are using in India is the boiling water reactor. Now here fuel again is enriched uranium, moderator and coolant this time is normal water, not heavy water. Now the fact about boiling water reactors is that these were the first reactors to be used by India. Before we started using pressurized heavy water reactors, the first two Indian reactors were boiling water reactors. All right, the first two Indian reactors were boiling water reactors, and then after that, once we understood about pressurized heavy water reactors and how better they are in terms of efficiency and the use, this is when we switched to pressurized heavy water reactor. But before that, the very first two reactors that India started using, they were boiling water reactors. So design wise, they are simpler. Design wise, they are simpler. As you can see here, that this time you do not need a steam generator. Here, if you look at the previous design, we needed a steam generator because you had heavy water which was pressurized. So we need steam generator so that we can convert this water into steam. But this time we don't need to do that because as soon as you start producing heat, water comes in contact with the heat and starts to convert into steam. And again, the same steam will go to a turbine. From the turbine, it will go to a condenser. And why condenser? I forgot to tell you there. Why condenser? So that we can change the steam back to water, right? So that we can change the steam back to water. So this is the role of a condenser. So in this manner, you are generating steam and that steam is directly going to the turbine. So a simpler design, but not as efficient as the pressurized heavy water reactors are. Then after that, we have a very crucial reactor from Indian perspective, and these are fast breeder reactors. And from the perspective of your examination, from the perspective of your prelims and mains examinations, I would say that fast breeder reactor is very, very important for those of you who are writing the exam this year. And if the question doesn't come this year, expect it next year. But I am expecting that they should ask something based on fast breeder reactors or at least nuclear energy in general, because the amount of news articles that we have seen regarding fast breeder reactors and nuclear energy in general in the last 1 year has been much more than whatever we have seen in the past 5 years. So that's why, in this context, when we look at this particular chapter or this part of the chapter, I would say that this time this part of the chapter is very important. And in that, especially fast breeder reactors are very crucial. Now, first, let's try to understand what are fast breeder reactors, and then I'll come to why are they important this year for your examination. So, very first thing is fast breeder reactor. The name fast breeder reactor. What is the meaning? The first term is fast. Why fast? Because these are fast reactors. Why are they fast? Because here we do not control the speed of neutrons. What we discussed in pressurized heavy water reactors, that also applies in boiling water reactors, is that we control the speed of the reactor. Sorry, control the speed of the neutron. And what do we use to control the speed of the neutron? What is required for controlling the speed of the neutron? Yes, moderator, correct? So moderators are required for controlling the speed of the neutron. Now, if we are saying that these are reactors where we let the neutrons travel at faster speed, it means that we won't use any moderator. So that's why this is what we do. That these are the ones, they don't use moderators, and therefore most of the fission produced are produced by fast neutrons. All right, we are using fast neutrons to produce the reaction, to make fission happen. Now in this particular scenario, the coolant also is different. The coolant that we use here is liquid sodium. All right, liquid sodium is being used. Now the second term is breeder. Why the term breeder? So the name breeder has been given due to the fact that the reactor produces more amount of fissile material than it consumes in operation, meaning that it generates more new fuel than the fuel that it spends. Meaning what? That if you are using 100 grams of fuel, you are getting 150 grams of fuel back. Just imagine just imagine that if this was your scooter or bike or your car, that you go to a petrol pump, get 1 liter of petrol in it, and as you start driving your car or your scooter, the 1 liter of petrol, it starts to convert into 1.5 liters of petrol. It starts producing more of petrol. What else do you need in life? Correct, if that was possible in terms of petrol. Unfortunately, that doesn't happen in terms of petrol or any common fuel that we use. But it happens here in this reactor, that the fuel that you are using, the fuel produces more of itself. That if you have used 100 grams of plutonium, you get back 150 grams of plutonium, and you keep using that for as much time as you want. So that is something which is very unique about breeder reactors. Now in this particular scenario, that's why when it comes to the fast breeder reactors, they are said to be the future. They are said to be the future. And if you remember, in the very first class, when we had started discussing about energy, I had told you that nuclear energy is at a very different spot. That we can call it as renewable, we can call it as non-renewable. Now this is where the reasons begin. When would we call it as non-renewable? In the current scenario. In the current scenario, where most of the fuel, or rather most of the nuclear uh, fuel that we are using is uranium, and uranium has a finite quantity. The nuclear reactors that we are using are largely pressurized heavy water reactors or boiling water reactors or some of the other designs. So they all, if they are being used with uranium, then in that case nuclear energy is non-renewable, correct? But the second case is when you start using nuclear fusion, because once we start using nuclear fusion, the kind of energy that we'll be able to produce, we don't have to be bothered about any other energy source. This entire big bulky chapter that we are discussing will be all about nuclear fusion and fusion only and nothing else, because then you will not need anything else if fusion becomes possible, if it becomes practically commercially viable. So that makes nuclear energy renewable. At the same time, the fast breeder reactors also make it renewable, because they are going to produce more fuel than what they are consuming. So then they can start running for a very long time. And that is why fast breeder reactors are so important. So that's why when we look at nuclear energy, that's why we have these two perspectives. Now, this is a typical diagram of a fast breeder reactor. Don't worry about this. Don't close this lecture here. This is pretty same, similar to what we discussed in our block diagram also. You have the same core, you have the same control rods, you have the same steam generator, you have the same pump, you have the same turbine, so you have the same condenser. Everything remains the same. Just that it looks more scary than the block diagram that we had seen. So that's why overall, this is basically what happens in terms of the fast breeder reactors. that this is where we do not use any moderator, so that the neutrons are traveling at faster speed, and that is a requirement for making them work. Now, coming to why exactly am I saying that this year fast breeder reactors are important? This is a news from that I've taken from PIB, 4th of March 2024. PM witnesses the historic commencement of core loading as at India's first indigenous fast breeder reactor at Kalpakam in Tamil Nadu. Now, until now, when it comes to India, we have had two fast breeder reactors. The first fast breeder reactor that has been operational for some time is fast breeder test reactor. Fast breeder test reactor. Now, this reactor has been functional for more than 20 years now, although it's a small scale reactor, but this is something that we started working on, and we started testing the fast breeder reactors or the technology behind fast breeder reactors. So that's why this became very crucial from the perspective of the future of energy in India. Then the second one is prototype fast breeder reactor. Prototype fast breeder reactor. Now, this prototype fast breeder reactor is the second reactor that we have developed. Now, although the completion of this reactor almost had happened back in 2012 itself, but there were certain concerns with regards to the safety and the security of this reactor. So it took some time, because uh, it's very hilarious what happened. 2012, when the present government was in the opposition, they had asked a question. They had raised a question in the parliament, and they had asked the then UPA government that what is the status of this fast breeder reactor? When is it going to be operational? So the government back in 2012 had answered saying that, look, this is almost done. There are certain concerns that we are looking after, and we expect that in 1.5 years it should be ready. Then 10 years later, in 2022, when the seats were exchanged, when the NDA came to power and UPA was in opposition, UPA raised this question: what is the status of this fast breeder reactor? And they got the same answer that they had given 10 years back. It's almost complete. There are certain safety features that we are testing. It should be ready in next 1.5 years. So the government's changed, the answer did not. But finally, we see that we are in a position where this is now ready. This is now ready, where we see that after completion of core loading, the first approach to criticality will be achieved, leading to generation of power subsequently. And we discussed about criticality yesterday, that once we have determined the critical mass, we can start the operation of any given reactor. So this is exactly where we are, that the prototype fast breeder reactor is now ready, and this is going to be very, very crucial in ensuring the future of energy in India. And this is a 500 megawatt power plant that is based on fast breeder reactor technology. So this is basically where we are right now, and because of this very news, I am saying that this has become a very, very important topic in this year's examination, and if not this year, then next year. So but we should expect a question to come from here. Now, coming to India's nuclear program, but before that, if you have any question from whatever we have discussed until now, please let me know, and then we shall go forward. So, can you state the two reason about how nuclear reactor could be renewable? Okay. So see, there are two perspectives. There are two perspectives. So one is about nuclear as non-renewable. Nuclear as non-renewable. So this is where we are talking about uranium based reactors. All right. Why? Because uranium is finite mineral inside the Earth's crust. So once uranium is over, you are done. And when it comes to nuclear as renewable, then here we are talking about two perspectives. One, nuclear fusion, because with very small quantity of hydrogen you get enormous amount of energy, and that too hydrogen, which is so amply available on the earth. So that's why once we are able to use, once we understand how to use them commercially, will be done forever. So one perspective there is nuclear fusion. The second perspective there is fast breeder reactors. Right. The second perspective there is fast breeder reactors, because fast breeder reactors will be able to produce more fuel than what they are consuming. So if we had ample number of fast breeder reactors, we'll be able to keep on producing fuel from here itself. So we do not need new fuel. So that is exactly what we are saying in terms of why nuclear can be called as renewable. I hope this answers your question. Explain criticality once again. Criticality is where we are saying that we have been able to determine the critical mass in any given reactor. And critical mass is that mass of any nuclear fuel at which you can run a controlled chain reaction. So criticality, let me just write this again so that there is no confusion about it. So criticality is when a reactor reaches or determines its critical mass for a sustained or a sustainable controlled chain reaction for electricity generation. Fission is non-renewable energy. As we discussed, it can be seen as both. What was Bhopal gas tragedy? So, see, Bhopal gas tragedy actually was not related to nuclear energy. It was actually a tragedy where certain poisonous chemicals, they from manufacturing plants, they were emitted, and they basically merged, or they actually uh, were emitted into the atmosphere, and they made the entire air poisonous in Bhopal, and unfortunately led to the deaths of a lot of people there. So that was chemical in nature and not nuclear. Does India have fast breeder reactor? Yes, of course. We just discussed that there are two fast breeder reactors that India has: fast breeder test reactor and now prototype fast breeder reactors. Not understood working of these reactors. Can you please describe it again in short? So what we basically are saying is that any reactor that we have, there are basic parts of any given reactor. So at the core, the nuclear reactions would happen. That is, the nuclear fission happens at the core, and all the heat energy that is generated, that will be carried by the coolant towards the turbine. And to control the number of neutrons, you have the control rod. To control the speed of the neutrons, you have the moderator. So that's why these all become the important points of any given nuclear reactor. The moderator will carry condensed back to the reactor. Not the moderator, it will be through the pump. So it is not moderator anymore. Moderator is where you have this water inside the core itself. Why is it required to not boil water and keep its boiling point above using high pressure? That's what I told you, that its heat carrying capacity increases. Steam doesn't carry as much heat as liquid water can. That's why. Where is the moderator? Moderator is located at the core. Explain me turbine, sir. So turbine basically is that part of the reactor where the turbine basically will do what? This is where you would have an alternator connected to this turbine, and this is where electricity generation happens. The movement, the movement of the turbine leads to the energy being produced, and that is where you can create the electric, or you generate the electric current. Cyanide carbide. Yeah, it was methyl isocyanate gas that we had in the Bhopal gas tragedy. In all the reactors, nuclear energy is converted to heat energy, and using steam, the electricity is produced. Is this the common method in this reactor? Yes. In more or less all the reactor types, this is a very common method that we are using. And not only in nuclear reactors, even in coal fired thermal power plant, where we are using coal to produce electricity, there also the same way you are using it. You heat the coal combustion happens, then you have the boiler where water converts into steam, and that steam is carried to the turbine. Same. In geothermal energy also we saw the same thing, that the turbine is where the steam is being carried, leads to a rotation of turbine. Same. So in many of these cases you will find that the usage of turbine is, of course, hydroelectricity power plants also have the turbines. Could you go back to the criticality page? Criticality is here. Nuclear reactors form electricity. Yes, it does generate electricity. Do we have to draw the diagram of nuclear reactors along with the answers? Not necessarily. The maximum that you can do is draw a block diagram. The very first diagram that we had seen at today's class, that's enough. Don't go beyond that. Why we need to control the number of neutrons? Does it increase in the process? See, if you remember yesterday, we had discussed that from one neutron you produce three, from three it will produce 9, 27, and so on, right? So then what happens is that you set up a chain reaction, and here the amount of energy that is being produced at every step is enormous amount of energy, and it is just multiplying, right? It is multiplying exponentially at each and every step. So that is why we need to control the number of neutrons, otherwise the reaction goes uncontrolled, and instead of producing electricity you will be creating an atom bomb. So that's the difference, and that is why we need to control the number of neutrons. Is only neutrons present in these reactions? I mean, neutrons are crucial mainly for the energy, the speed that they are at. So, as many of the biofuels or nuclear reactors are government establishments, there have been in news about public agitation in regard to construction of ethanol plants, but the voices of public or farmers are not considered during the EIA or public hearing. Not correct entirely. And also there is one thing, when it, especially when it comes to nuclear energy, the way we have been seeing nuclear energy is a very different lens. Nuclear energy always has been seen to be something that people should be afraid of, that everyone should be afraid of nuclear energy. it can be catastrophic, it can cause so many deaths, it can take so many lives. So we see that there are all these m- a lot of it I would also call as misconceptions about nuclear energy, because the way in which an atom bomb works versus the way in which nuclear energy works for electricity generation is very different. There are n number of safety features that are kept at place to ensure that nothing goes wrong. And that's why, if you just count the numbers, when an accident would have happened in a nuclear energy power plant, one is in Chernobyl, one has been in the US, one has been in Japan. And in all these three cases, even if you combine all these three cases, the number of deaths, if let's say that's the crude way of counting the harm, if you count the number of deaths, it's not beyond 10,000. Let me be crude here and talk about the number of people who have died. The number is not beyond 10,000. But then, on the other hand, consider coal, consider petroleum, and the number of people who are dying every year because of that. It's not that they are dying in an accident or something. People die in the accidents, unfortunately, in the coal mines also. But that never stopped anyone from getting electricity from coal. Now, this coal or this petroleum, because of air pollution, because of global warming, is leading to serious health concerns. And look at the number of people who have lost their lives just because of air pollution, because of the problems created in the body due to air pollution. The number goes beyond lakhs. So, on one hand, we are talking about being afraid of something where 5,000 to 10,000 deaths might have happened. And on the other hand, we are very easily using something that has led to more than lakhs of people dying. So it's about perspectives and how people always have been afraid, and there have been a lot of negative sentiments against nuclear energy. So which is, I believe, which is not entirely well placed always. So that's why a lot of education is also required about these things, that people need to understand that there are so many things that are being done to ensure that nothing goes wrong in a nuclear reactor. And apart from three cases that we see, one in the US, one in Ukraine in Chernobyl, and one in Japan, apart from that there haven't been any cases where we have seen any kind of problem. So that's why it's a perspective that we need to look upon. How is it possible that through turbine movement electricity energy is generated? I mean, this is how basic electricity works, where you are creating that condition for electric current or the movement of electric current, the production of electric charge, which will actually lead to electricity generation. And basically it starts with kinetic energy, and this kinetic energy is converted into electricity. If we are able to find criticality leads to explosion, not explosion, but leakages are possible. So that's why we take every step possible, but explosion wouldn't happen. What will happen with controlling the speed of neutrons? The chances of getting energy or the chances of creating fusion becomes higher. What was the Chernobyl accident? How it occurred? It basically occurred because they did not control the pressure. They saw that the pressure was increasing beyond the permissible limit, yet they thought that they'll be able to control it, and they did not take any measures to control it actively, and that led to leakage or a nuclear accident happening there. So it was something that could have been controlled very easily, just that they were under pressure also to do more, to produce more, and in that scenario they took that step that they should not have taken. They had the chance to actually decrease the pressure and control the pressure, but they did not do that. Why fast breeder reactors neutrons are not controlled? The reason is not very straightforward for me to explain you, because the way fast breeder reactors work is very different from the basic working of pressurized heavy water reactors and others. So let's not go there. I don't think they can even ask this question. Many of the sugar industries in India are establishing ethanol distilleries by stating extension of the existing industry. Since this project is an extension and not a new establishment, the government is avoiding getting new environmental clearance. So, isn't it a lack of rules and regulations in this regard, apart from advancement need of proper protocols is mandatory? I completely agree with this because see, there have been a lot of problems when it comes to the environmental impact assessment rules in India. There are a lot of gaps, and these gaps have to be filled. Because many times what happens is that we see that the governments take a step where they promote infrastructure development, they promote industries at the cost of environment, at the cost of environmental health, which is wrong, which is completely wrong, because long term effects of environmental hazards are pretty bad. And that's why the rules and regulations have to be tighter. And that's why if you go back to 2020, you'll find that in 2020 there were new draft rules of environmental impact assessment that were brought forward by the government, and it was heavily criticized by experts all across, environmentalists, advocates, everywhere. We saw that there were huge criticisms that happened back in 2020, because these new environmental impact assessment rules were making the entire rules even easier for the industries to exist at the cost of the environment. So, yes, is there a gap in the rules? There is. Do we need to do something about it? We need to do, and that's why public participation in this becomes very, very crucial. Public awareness becomes very, very crucial. That's why in case of when it comes to environment, there is an entire chapter that we read about environmental awareness, which becomes very crucial for us, because otherwise we do not understand the kind of role that we need to play or we can play. Unfortunately, we are doing the least probably possible, or maybe even not the least, if it is not easy for us. I'll give you one simple example. I know I'm digressing a bit from what we are discussing here. I'm sure that many of you are using RO filters, reverse osmosis filters, at your home for filtration. Have you seen how much water it wastes? Do you know how much water do you are wasting on a daily basis just because you are using RO water? You'll see that constantly the filtered out water will just go in your sink or maybe in your wash basins or wherever. And what happens? You are simply wasting water. For every liter of water, all right, every liter of filtered water that you get out of an RO filter, at least 1.5 liters are being wasted. So for every, if let's say you have a capacity of 20 liters of that RO filter, it is wasting 30 liters of water. So in a day per household, probably 60 liters of water are being wasted. Can you not use it? Is that water not reusable? It is absolutely reusable. Can you not use it for washing utensils? You can you not use it for cleaning the floors? You can. Washing clothes? You can. But unfortunately, that needs an extra step from your end, that every day you will gather that water, you will use that water and use it for whatever you can, so that you can save some water. So, unfortunately, I'm not sure how many of us are actually doing that. I do. I have been doing that since the time I've been using RO filter. But unfortunately, this is something that it's simply ignored. It's an ignored part of your life. When it comes to electricity saving, why do you save electricity? So that the bills are lesser. But do you know the environmental cost of not saving electricity? That how much pressure you are putting on your resources if you are not saving electricity? Think upon it. So, unfortunately, that's why public awareness is a very crucial part of all this. Anyway, coming back to our discussion, we can collect wastewater for other purposes like mopping, laundry. Exactly my point. 1 liter of RO wastes 4 liters. See, depends on, I mean, the what kind of water you have, whether you are getting good enough water or not. uh, there is something called as TDS, total dissolved solid. So very first thing that one should do is just check the TDS, with a TDS meter. Just check the TDS value of the water that you are consuming. If the TDS water is near 100 or 100 150, it is fine. because that means that it has the essential minerals that are required. Unfortunately, what happens is when you over filter that water with the help of RO filters or whatever you are using, the TDS levels might drop down to 40s to 60s. And if you are drinking water which has a level of 40s to 60s, it is bad, because you are just getting water that is needed, but your body is not getting the electrolytes. It's not getting the minerals that automatically it should get from you drinking water. So that's why TDS levels of water should be near about 100 or 100, 120, etc. That is good. Up to 150, even up to 200 is consumable. But beyond that is bad water, I mean, not drinkable. Then it has to be filtered properly. So that's why it depends on the TDS value of what you are consuming. So, for example, the tap water that I am getting at my home, it has a TDS value of somewhere around 125 to 130, etc., which is, I would say, drinkable without using an RO filter. I realized this later, that even if you are using a simple candle filter, that's enough, or even if you are using a simple UV filter, that's enough. So that depends on what kind of water, or whether you are getting a filtered water or what exactly are you getting. Let's come back. Let's come back to our discussion. So now we are discussing about India's nuclear program. Now, when it comes to India's nuclear program, what we have is something called as India's three-stage nuclear program. Three-stage nuclear program. So we have the first stage, we have the second stage, and we have the third stage. Sorry. Now, what we mean by these three-stage nuclear program, what is this program, and why is this program? Let's try to understand these two things. So, first, what is this program? This is a program where we have devised three stages of our nuclear program, where in the first stage we are using pressurized heavy water reactor. In the second stage we want to use fast breeder reactors, and in the third stage we want to use thorium based reactors. And this is where India is developing advanced heavy water reactors, right? Advanced heavy water reactors. So for the third stage we are developing this right now. Now, when it comes to the three stages of India's nuclear program, our end goal is to start using thorium instead of uranium. All right, the end goal is to use thorium instead of uranium. Thorium instead of uranium for energy generation. Now, why thorium? Because India does not have a lot of uranium. The uranium that we are using in our nuclear reactors, largely it is being imported. But when it comes to thorium, India has one of the largest reserves of thorium in the world. Some of the data will tell you that India has the second largest reserve of thorium in the world. Some will say fifth largest, etc. I would want to believe second largest. So India is among the uh, countries with biggest deposits of thorium. So now we want to create a condition under which we can start using thorium as our nuclear reactor, so nuclear fuel. But that's not possible directly. That you might think that, okay, fine, then start using thorium. What's the problem? The problem is that thorium is not directly fissile as uranium is. We discussed yesterday that uranium is the only natural material which has a natural capacity to undergo fission. Thorium can be made fissile, meaning that you can start making thorium to behave like fission is possible in that. So you can convert thorium into something so that you can start getting energy, but that cannot be done directly. So to achieve that goal, we devised this three stage nuclear program. Now, in this particular scenario, when it comes to the nuclear program, this is a program that we had planned back in 1960s itself. And this is where the role of Dr. Homi Jahangir Bhabha comes here. Now, Dr. Homi Jahangir Bhabha, apart from him, some of the other scientists in the post-independent India, just after our independence, these were some of the scientists who have been very crucial in the scientific development of this country. And Dr. Homi Jahangir Bhabha has played a very, very phenomenal role in ensuring that India develops its nuclear capacity, not only in energy generation, but also in weaponry. Now, he was a very, you can say, big advocate of using nuclear energy. Even just after independence, he had started suggesting the government of India, and notably our Prime Minister back then, Pandit Jawaharlal Nehru, he had started advocating for the use of nuclear energy. Now, back in 1947, 1948, nuclear energy was not a term that anyone wanted to hear, because it was just 2, 3 years back when the world saw what nuclear energy can do, what an atom bomb can do. And we saw the kinds of deaths that happened there. So, in Japan. So, that's why nobody wanted to experiment. Nobody wanted to do anything with nuclear energy because it was very controversial topic back then. And this is when Dr. Bhabha started suggesting that India should look away, move beyond coal, and start looking towards nuclear energy as our energy option. Nobody supported, neither the opposition, of course, nor uh, uh, the people who were there in the government, who were a part of the Congress party back then. Even they did not support, apart from maybe the prime minister of the country, who was the only one probably at that point of time who was supporting, or who was at least listening to Dr. Homi Jahangir Bhabha. And nobody else was interested, nobody wanted to touch that topic. But he started working. Dr. Bhabha started working. He also started working with the Soviet Union back then to generate the capacity in India, to create the capacity in India. And then finally he was able to achieve that. He finally was able to get the approval from the government of India, and then started working on India's nuclear program. He started working on getting energy, generating energy through nuclear energy in India back in 1960s itself. And he was moving very fast. That first he started advocating for energy generation using nuclear energy, and then at the same time, because we had seen so many wars in the first 15 odd years after our independence, 1948 against Pakistan, 1962 against China, 1965 again against Pakistan. So this is when he started advocating that, look, we have to be very strong. We have to at least look very strong, and that strength also comes from nuclear energy. That strength also comes from nuclear weapons. And also parallelly he started working on nuclear weapons. So he was working very fast back then, and it was good for India, because at one hand we were looking at energy security, and on the other hand we were also looking at our defense. And he was somebody who was working everywhere. This is also something that was not liked by many of the Western countries, including, of course, the US. Dr. Bhabha died early. He died in a crash, in a plane crash. And this was, I think, 1966, when he lost his life to this accident. Many of the reports also believe that this accident was not something that just happened. This was an accident where there were players behind it. The Central Intelligence Agency of the US, popularly known as the CIA, might have orchestrated this accident, which led to the death of Dr. Bhabha so early. When he was moving so fast, he was being ambitious for India, for our country. So, unfortunately, did not live for very long and died in that accident. But he initiated this program. He was the one who thought through the program that India needs to have these 3 stages, so that by the end of the 3 stages, we become energy independent. We start using thorium, and we are not bothered about who has uranium and who doesn't. We don't have to sign any pacts with everyone. We will become self sufficient, and we will be the one who will start exporting thorium to the others who need. So that's why, with all that view in mind, he devised this entire plan in the 1960s itself. So, what are the 3 stages? The first stage that we have are the conventional nuclear reactors, where we are using pressurized heavy water reactors. We are using pressurized heavy water reactors where we'll be using natural uranium, that is uranium 235 will be used, right? Uranium 235 will be used, and as a byproduct we get plutonium. As a byproduct we get plutonium, and this plutonium that we are getting, this will be used in the fast breeder reactors in stage 2. And as you can see that this plutonium produces more of plutonium, right? This produces more of plutonium. Now this is where we also introduce thorium. We are also introducing thorium in the second stage. Now this thorium is not being used as a fuel, but rather what we are doing is something called as irradiation. Irradiation of thorium takes place. Now irradiation of thorium means that radiations are being passed through thorium so that we can make it, or we can convert it to uranium 233. We are converting thorium to uranium 233. Now can we not directly use uranium 233? The answer is not. We cannot. Why? Because uranium 233 is not natural. If you remember, yesterday we discussed that natural uranium only contains uranium 235 and uranium 238. Uranium 233 is something that we produce out of these operations. Right? These kind of reactions lead to the production of uranium 233. Otherwise, uranium 233 is not natural. It is not naturally occurring like uranium 235 or uranium 238. So this uranium 233 will be used in the third stage, where we will have advanced heavy water reactors. We will use advanced heavy water reactors. So again, uranium 233 will be used. It will produce more of uranium 233, plus thorium is producing more of uranium 233. So now it becomes self-sufficient. So estimates are that if we use this stage 1 for 30 years in operation, if we use stage 2 also for another 30 years, we produce enough fuel to be used for the next 500 years. For the next 500 years we'll have enough energy, we would have produced enough fuel to run it for the next 500 years. So 30 years in stage 1 plus 30 years in stage 2 means 500 years in stage 3. That is the beauty of fast breeder reactors, why we are looking at fast breeder reactors as an answer. So this is basically what happens in these 3 stages of our nuclear program. So the first stage, so in the first stage, what are we doing? Uranium 235 is used as fuel for pressurized heavy water reactors. Plutonium is the byproduct, which becomes fuel for the second stage. All right. In the second stage, plutonium is used as fuel in fast breeder reactors. Irradiation of thorium, that is thorium 232, meaning passing radiations through it, All right, passing radiations through it. Irradiation of thorium 232 produces uranium 233. All right, produces uranium 233. Byproduct or byproducts are plutonium and uranium 233, where plutonium is reused as fuel for the second stage, and uranium 233 becomes the fuel for the third stage. So now coming to the third stage. So in the third stage, we are using uranium 233, thorium 232 cycle as fuel. Irradiation of thorium 232 further produces more uranium 233. So this is basically how we for this is basically advanced heavy water reactors. So and creates a sustainable chain. So this is basically how the third stage is supposed to be used. So now by the time we are in the third stage, we will be able to use thorium and we will not need any more uranium. All right. We will not need any more uranium. So that is basically what will happen by the time we are in the third stage. Now, lastly, coming to the applications of nuclear technology, how exactly do we look at the applications? First, of course, something that we have been discussing, that it can be used for energy production, basically for electricity, right? For electricity generation using nuclear fission and nuclear fusion, both. So right now, nuclear fission, in the future, nuclear fusion as well. Then agricultural applications, we can make its use for water use and soil management. We can make its use for pest control. We can use it for animal health and security or productivity. For food safety, we have nuclear fertilizers. We can do soil salinity control. So there are all these things that we can do with agricultural applications. So for example, we have nitrogen 15 as a fertilizer. So nitrogen 15 is radioactive. So it's a radioactive fertilizer. But this helps us in understanding the optimum amount of fertilizer requirement for a soil. So helps us understand optimum fertilizer requirement for any plant or any soil. So that's why nuclear fertilizers are there. Then after that, we have something called as carbon dating. Now with the help of carbon dating, we are able to, it allows us to accurately date the historical artifacts, that will be able to understand what the age of historical artifacts are up to 50,000 to 60,000 years. So anything that is up to 60,000 years old, we will be able to accurately age or predict the age of it with the help of carbon 14. because carbon 14 is also radioactive. So that's why we will be counting the age with regard to how much of carbon 14 has been lost in these many years. So that can help us in calculating the age. Then in industrial applications, we see that there are various different ways in which they can be used. They are used in non-destructive testing to test the strength of the material basically, and hence they can enhance the material quality in electrostatic control, in radioactive tracers, in oil and gas explorations. So there are various different ways in which they are used. Then in medical applications also, we know that they are very crucial in radiology, and they are used in various different applications in radiology as well. So in cancer treatment, for example, we make the use of uh, radioactive elements. And then also for space exploration, we see that they are very, very useful in space exploration also, where, for example, there is something called as radioisotope thermoelectric generator. Now, this is also that is something that has been developed by ISRO now and becomes very crucial because it will help in supplying the power and heating to any space vehicle, where we are making the use of plutonium 238 in this process. So that's why we see that there are various different ways in which we can make the use of nuclear technology, and hence it becomes very crucial, and it goes beyond just electricity production or being used as a weapon. Now, one thing that I've done, I've shared with the team a list of important radioactive elements, important radioactive elements, and also the fact sheet about the applications, the factual portion of what the applications of nuclear technology are. So just go through it. All right, just go through it, and this will help you because these are factual portions. So you should just read upon it. So it's a 5-page PDF document that I've shared. Please just go through it. The team will share it with you. All right. So this is the end of this chapter. Now let's take the questions after the break. Right now, if you have any doubts from India's nuclear program and applications that we discussed. How nuclear technology helps in food safety. See, it is mainly with the help of radiations, because what we do is that with the help of radiations, if there is any pest or any microbe that is growing in the food, that can be killed. Controlled amount of radiations, not a lot, controlled amount of radiations are used to kill these microorganisms or decomposers, and hence it is able to provide us food safety and also prolong the age of any food. Irradiation, as we just discussed, irradiation means when you are passing radiations through anything, any matter. So even when I just spoke of food safety, when you are passing radiation through it, that is also called as irradiation. What will happen to the products of fission of uranium 235 such as krypton and barium? Nothing will happen to it. They are just produced in the operations. They do not really have any significant significance for us as such. Now, are we in second stage? Still early days to say that we are in the second stage. I would still say that we are in the first stage. We still are in the first stage because we just have operationalized our second stage or the fast breeder reactors. So it wouldn't be wise to say that we are in the second stage. We are still in the first stage. Largely, we are in the first stage. Why their word use cycle? Cycle, because it's a cycle that we are producing of irradiation, getting the byproduct, and being used as a fuel. So that's why it's a cycle. Carbon dating. Carbon dating basically is the use of carbon 14, the radioactive carbon, to find the age of any historical artifact. Why will we, what will we do of uranium 233? Is that as effective as uranium 235? Yeah, see, effectiveness wise, there is no problem with uranium 233, and it is something that can be used as fuel very well. And that too, because we are producing it from thorium, it becomes highly cost effective. Disadvantages of nuclear energy. The very first thing is the misuse of nuclear technology, the misuse in creating weapons, and how it can cause humanitarian crisis. Then at the same time, nuclear waste, the disposal of nuclear waste many a times also becomes a big challenge. And then the technological challenges, because it's not easy to get it's not easy to get energy from nuclear sources. Please write doctor name. Oh, he's not a doctor, he's a scientist. Doctor because he has done PhD. That's why when you do PhD, you also qualify to be called as a doctor. So his name is Dr. Homi Jahangir Bhava, a name that is very, very important. The team shared two-page PDF. I'll just check if there's any confusion there. I'll check it. So let me take a break here. The time is 6:25. Can we be back by 6:35? Let's be back by 6:35 and continue our discussion from there on. We'll discuss the mains questions first, and then after that we'll move forward. Welcome back, everyone. So let's first start with the questions that we have seen from this chapter in your mains examination. We have taken some examples of the questions that you've seen in your prelims, but this time we are looking at some questions that you've got in your mains exams. Now, first thing, when it comes to these questions, many a times the questions that we get, they are direct in nature, where simply you have to describe something, just write a short note on something. But sometimes the questions are layered, where we have to understand that there are different points of views, there are different aspects, and all those things have to be kept here in a very balanced way. Now, I'll give you some examples of from these questions that we have seen from this chapter. How exactly do we do that? So if you look at the first question, do you think India will meet 50% of its energy needs from renewable energy by 2030? Justify your answer. How will the shift of subsidies from fossil fuels to renewables help achieve the above objective? Explain. Now, if you see, there are two parts, right? This is one part, and this is the second part, right? Now, the first part is, do you think India will meet? Now, this answer cannot be no, right? This one thing is that this is not a yes or no question. You cannot simply say yes, India will do everything, thinking that okay, government will reward you extra marks because you have written something in the favor of the government. So that's not going to happen. On the other hand, you cannot write no. India can't. That you cannot do. So that's why it's not a simple yes or no question. All right. It's not a simple yes or no question. This is where you have to present the present facts. Where are we right now? What are the targets that we have kept? And how do we wish to achieve those targets? What are we doing to achieve those targets? Are there things being done by the government of India? Are there initiatives that are being taken? Are there programs and policies that are being adopted? So you'll have to give those examples as well. You have to substantiate those examples so that you with those examples so that you are providing a holistic answer. So that's why we know that India has kept a target that by 2030 we want that 50% of our energy needs should come from energy, I mean by renewable energy. Now what are we doing for that? So, in terms of solar energy, what are we doing? In terms of wind energy, what are we doing? What are the targets? What is the current capacity? What are the programs and policies? In case of biofuels, what are we doing? So, just write about all this. Then we also have the green hydrogen mission that we have now adopted. So, what is this green hydrogen mission? Write about that as well. So, there are all these things that we have to write about. Where are we? And then mention about the other sources like nuclear or hydroelectricity power plants. So in that, say that these are non-fossil sources. That what are we doing with other non-fossil sources and how do we wish to achieve these targets? So that's where write about all this. Now I've not mentioned two of the sources here. I've not mentioned geothermal. I've not mentioned offshore. Why? Because right now they are in a very nascent stage. We can't keep targets, right? We can't keep targets with them. With solar energy, we are looking at 280 gigawatt. With wind energy, we are looking at least 150, 140 gigawatt. With biofuels, we are looking at 30 gigawatt. Green hydrogen, 125 gigawatt. Nuclear energy, almost 20 gigawatt, 10 gigawatt at least. So compared to that, with geothermal, some megawatts. With offshore energy, some megawatts. So that's why I'm not considering them as a part of our targets. All right. But as a part of the targets, we have all this. So you have to write that, okay, this is what we are doing in these energy sectors. And if we keep moving in a manner that we are doing, we of course can get to the required target. And then also mention the policies and the programs. Like there is the rooftop solar mission or there is the national solar mission. Then what are we doing with wind energy? What is national biofuel policy doing here? So there are all these things that you have to mention so that you can substantiate your answer well. Now the second part of the question is, how will the shift of subsidies from fossil fuels to renewables help achieve the above objectives? Explain. Now subsidies, what do subsidies do? They provide kind of a financial help, correct? So that you spend more and government is spending on your behalf by providing some subsidies. Now whichever sector gets the subsidy, obviously more businesses, more people, more employment will work towards that sector, correct? It will start moving towards that sector. So if let's say fossil fuel is getting all the subsidies, then of course more businesses, more companies would want to establish themselves with the fossil fuels. But if let's say the same subsidies, they are shifting towards solar energy, they are shifting towards wind energy, then in that case the companies would also want to shift their businesses there. So that's why automatically you start creating an economic environment by creating or shifting these subsidies to the renewable sources of energy. So this is how it will also help in the further improvement and growth of the new renewable energy sector in India. So that's why these are some of the points that you can write in this particular answer. Then the second question. Now, interestingly, this question was asked in GS paper 1. This was not asked in GS3. This was asked in GS1. Examine the potential of wind energy in India and explain the reasons for their limited spatial spread. So, potential of wind energy in India. So, potential wise, of course, you can write about the coastal states and how we can build the potential there. You can write about Rajasthan and being a wide open desert area, how we can use Rajasthan. And then also start mentioning offshore, because we are talking about a potential. So then offshore wind energy in India also has a potential. So that's why, especially in the terms of two states, Tamil Nadu and Gujarat, mention that what are the initiatives that we are taking here. So in this particular scenario, there are all these things that can be done, and this is how you can explain the potential that India has. Also in terms of numbers, where are we, what is the total installed capacity that India has today, and what is the aim that we have, and how do we wish to achieve that aim. And then explain the reasons for limited spatial spread. Now, limited spatial spread, the very first reason is geography, correct? We need kind of very specific areas where wind energy generation will be better. So, geography is one reason. Finance is another reason. Establishment is not that easy. It takes a lot of effort. You also need to acquire land. So, that's another reason. Getting that acquisition of land is not that easy. So, then materials, parts, technologies, there are all these reasons which accumulate into not having a very big spatial spread. So that is basically what you have to write. Then the third question, Nobel Prize in Physics related to blue LEDs. So the question basically is, how has this invention impacted the everyday life of human beings? Now, in this particular question, we have to write about, now see, there is something interesting here, that it talks about Nobel Prize of 2014 and the question has been asked in 2021. Now, there was something unfortunate, I would say, that we saw while the analysis of the 2021 paper was being done. And we see that I was just looking around, and what I saw was that there were some websites and there were some channels and institutes who were also suggesting that, look, this is why we tell you that you need to know the last 10 years of current affairs, because they have asked you a current affairs of 2014 in 2021. So that's why you should know 10 years of current affairs. This is one of the worst suggestions that somebody can give you, to read 10 years worth of current affairs. Reading 10 years worth of current affairs means that you stop preparing for 2024 or 25, start preparing for 2027, 28. It's impossible to read and remember current affairs worth of 10 years. So that's why this would be a wrong suggestion. The most current affairs that one should do is maximum of 1.5 years. Don't go beyond 1.5 years. Yes, a couple of questions can come which are beyond last 1.5 years, but you can't predict that, and you can't prepare for that, because uh, the amount of time that you'll be wasting to get that extra current affairs, maybe just one question, you will be actually stopping yourself from solving five other questions that you could have done by reading extra from the static areas. So now, why this question? Because this is a question related to science and technology in everyday life, which is a part of your main syllabus. So that's why it is not shocking. This is not out of the place that they ask this question, because today LEDs have become a part and parcel of our lives. Whether it is for lighting, you might have seen that the tube lights or the bulbs, etc., they have been replaced with LEDs in our homes. The price of LED lights have gone drastically down. The electricity consumption that they do is very less as compared to the tube lights or the bulbs. The life cycle that they have is way higher as compared to the normal bulbs. So we see all these advantages, and these advantages do not stop here. A lot of electronic devices, they use LEDs. Your televisions, your mobile phones, your laptops, how are they lit? There is a backlight, and this backlight is also blue LED. The studio where I'm standing right now, there are lights all across me, and all these lights basically are LEDs. Before LED studio lights came in, we used to record the sessions in lights which actually were halogens. So one, electricity consumption of halogen was huge. Secondly, it would make the entire studio very hot. I can't even tell you how taking a class standing in that studio felt like, but had no option. But now there are LED studio lights which are available. So electronics, lighting, medical applications, agricultural applications, we see that there are all these different areas where blue LED has shown its immense potential, and that's why today we see that it is being used everywhere. This is where you can also mention certain initiatives. For example, the Pradhan Mantri Ujjwala Yojana, where the government started giving out free LEDs and also distributing LEDs and ensuring that the price of LEDs also falls. Something that was taken back in 2015-16. So there are all these things that can be written, and that is how you can make a holistic answer out of this. Now, question number 4 and 5 both are related to nuclear energy. With growing energy needs, should India keep on expanding its nuclear energy program? Discuss the facts and fears associated with nuclear energy. Now, can the answer be no? Can you say that with growing energy needs, India should not keep on expanding on its nuclear program? We have to expand our nuclear program. That is one of the ways how we can expand the non-fossil portfolio of energy that India has. So that's why we have to do that. But then comes the actual part of the question: facts and fears. The positives and the negatives. What are the advantages and the disadvantages of nuclear energy? So advantages wise, we know that it is something that is cleaner, it is something that is abundant, it can give you a lot of energy, a lot of potential lies with it. India has a lot of thorium, India is participating in ITER, so there are all these facts or all these advantages. Then the fears. Fears first: nuclear accidents, leakages, nuclear waste, health hazards, environmental hazards. So there are these points that have to be written in the fears part. So this is how you can balance your question or balance your answer. But remember that this question needs to have a positive conclusion. Positive conclusion. Don't end with a lot of negatives. Don't end with a lot of disadvantages and limitations. You talk about limitations and disadvantages, but at the same time, uh, at the end, you have to give a way forward. You have to give a positive conclusion when it comes to an answer like this. So that's why this is very, very crucial that you keep in mind that whenever you are writing any negative point, wherever you are writing negative points, if the question has demanded that you write negative points, you write it, no doubt about it. The problems that we are facing. So for example, even in the first question that we see, justifying your answer, here also you can write that, look, there are certain shortcomings, there are certain problems. So for example, we need to grow at a higher pace probably. Write about that, there's no problem with that. But whenever you write these points, always ensure that you end the conclusion on a positive note. You write the way forward in a positive way. And why am I saying that? Is it to please the government? Is it that the government is going to correct your answers and give you higher marks if you've written something positive? No. Criticizing is fine. Way forward is what I'm talking about. Conclusion is what I'm talking about. And why? Once you become a civil servant, you are supposed to solve problems, not talk about them. Suppose that you are a district collector, and then there are people who are coming to you with their problems. What do? Do you discuss the problem only with them and say, yeah, I understand you are facing these problems, thank you very much? Do you do that? or do you provide solutions to them? That is why you are there. That is why you have been selected. You are the ones who have to solve problems. Correct? So that approach is required here as well. That even if you are talking about negatives, even if you are talking about critical points, give the way forward. If you're saying that this is bad, this is bad, this is bad, this is bad, then say this could be done. This is what we can do. This is what the government can do. This is how things can change. But always end on a positive note. Don't end on a negative note. Remember this. Then the last question, give an account of growth and development of nuclear science and technology in India. What is the advantage of fast breeder reactor program in India? Now, in this particular scenario, when it comes to uh, India's, basically you have to write about India's nuclear program and the development of India's nuclear program. Also write about India's nuclear arsenal and that we are a nuclear capable nation. So write about all that, and then after that, advantages of fast breeder reactor, something that we just discussed half an hour ago. So the same things you have to write. Now, if you look at all the questions that have come in the mains examination, something that I told you in the first class itself while we were discussing the strategy for this paper, I told you that questions that you'll get in your prelims paper related to science and tech probably will be touch more difficult as compared to the questions that you get in your mains examination. In the mains examination, you'll always have enough points to write. In most of the questions, 9 out of 10 questions, you'll have enough points to write. It's just that how do you present the answer? What are the points that you're picking? Are you picking the right points? Are you missing out on something which is very, very crucial? So those are the things that will matter more. In the prelims examination, sometimes questions can be more difficult. So that's why, from the perspective of this particular subject, I would say that probably prelims is more difficult than the mains examination. Mains is always going to be easier for you. All right. So now we have our next chapter, and the next chapter is space technology. So any question from the questions that we discussed, all the main questions that we discussed? There must be a conformity between introduction and conclusion. Uh, see, in most of the questions, I would agree with that, but not necessarily. Many times, what happens is that a question that you get has three different parts. So you might start with something and you end on something else. So, for example, the question starts with a basic definition. What do you understand by nanotechnology? How is it helping in the health sector? So then your introduction there is just about what is nanotechnology, defining nanotechnology, the advantages of it, and then you end on health sector, and you write a conclusion based on the applications of nanotechnology. So that's why, in most of the cases, it is correct what you're saying, that if we have a conformity between the introduction and the conclusion, it helps. But in many of the questions, that's not possible, so we should not force it. All right, we should not force that we should end with a conformity here. Answers for these questions, if you want, you should write. I gave you the points. See, there is no standard answer. There is no standard answer. There are various ways in which you can represent the same points. I would suggest you write and submit. You submit it to maybe islive@byju's.com or targetis@byju's.com, or if you want, you can submit it to me, rashish.kumar@byju's.com. Do that instead of taking the answer from me. Submit the answer to me. How long should the introduction be? See, introduction largely, on an average, 20 to 30 words maximum is fine. That will start your answer well, and then you start writing the actual answer. Could you tell me mains answer writing practicing? See, practicing of the mains answer, as I just said, that you should start. I mean, uh, strategy wise, there are many general points that one can tell you, that do this, do that, this is the word limit, this is what you should do, this is the speed. But unless you start practicing, there is no way around it. Mains examination needs practice. Somebody who is regular, if you are able to write daily, wonderful. If you're not, at least weekly. At least weekly, one should write an answer. Submit those answers, get them corrected, get the feedback, try to understand what the feedback was, how can you improve the next time that you write an answer. But that only happens with practice. We see that a lot of candidates, a lot of aspirants, they look around for sample answers, for model answers. They never help. They never help. Because I can give you model answer for one question, how does it help you in the other question? I can't give you model answers to 500 questions, right? That is where you need to step up and you need to start writing. And when you write, you'll find that your mind starts opening up, you start gathering more points, you start writing better, your flow becomes better, your speed becomes better, and all these are the points that will actually help you in the paper. Me telling you the answer will never help. So that's why it's a request to all of you, a suggestion to all of you: start writing. Start writing, start submitting, start getting those feedbacks. That is the only way that will help you in getting more marks in your mains examination. There is no way around it apart from what I'm telling you. Unfortunately, and I'm being very blunt here, year after year, we keep saying the same thing to every batch that we go to. Unfortunately, not more than 10% of the class actually listens to it. You listen to it, you think that you are motivated enough, you think that okay, I'm going to start writing. Unfortunately, you don't. And even if you do, sometimes you just write one or two questions or one or two answers, and then after that it again, uh, you go back to the old pattern. Please don't do that. The only way to get more marks in your mains examination is practicing. The only way. In the prelims examination, that may not be the way. Even if you know very well, you will be able to tick mark the correct answer. But the mains examination needs practice, and only practice. So please do that. In FBR, advantages generate more fuel than the use any other point. No, that is precisely the most important point there, that you get more fuel than you are consuming. I've sent you two answers. You haven't checked. Please send me again if I might have missed, but I do correct all the papers that I get. So if that's the case, you please resend to it. Send to me. Don't you teach environment? I do teach environment as well whenever I have time. Were these questions from static or dynamic areas? Most of them from actually static areas only, but they were asked because of a reason, that there was something in the news and hence the question was asked. Please tell me the email ID to which we have to send the answers. So answers you can send to target ias at byju's.com, or even if you want, you can send it to iaslive at byju's.com. In my opinion, introduction should always reflect the present reality or current dynamics of that topic, that is the actual seeking of examiner. Uh, Saying that not always is the way. See, there are a lot of ways in which you can write an answer. This is one of the good approaches to write an answer, no doubt about it. But even if, let's say, the same points are there somewhere in your answer, or maybe if you're quoting something in the conclusion, it's still good. So that's why, because there is no straightforward one way to write a good answer. How many students are selected in UPSC 2023 from Byju's? We have a selection of around, I think, 100 to 120 students already, and I'll have to check with the team with the exact number. Yes, this time we did not advertise anything. That it has different financial reasons for that, but the results have been good as always. Mail ID I just told you. Hmm. So let's move on to our next chapter, which is space technology. And again, a chapter which is very, very crucial from both perspectives of prelims and mains examinations. Now, first, space technology perhaps is one chapter from where we expect a question to come every year without fail. I don't know if there is any other chapter in any other subject where we can say for sure that look, one question at least will come from this chapter. I'm not talking about the subject. I'm talking about this one chapter. Just look at all the previous year question papers, at least in the prelims examination. You'll find that every year in prelims, at least one question, if not two or three or four sometimes, just from one chapter, that is space technology. So that's why space technology perhaps is the most important chapter in the examination. I'm not talking about only science and technology. I'm talking about most important chapter in the prelims examination at least. And even in the mains examination, you'll find that almost every year one question does come in the mains examination also. Now, space technology, how exactly are we going to go about it? There are two parts into which we have divided this chapter. One part will be of space science, where we'll understand about the various different concepts which are related to the universe, the understanding of the universe, the composition of the universe, what is dark energy, what is dark matter, some of the celestial bodies like the sun, planets, etc. So we'll discuss all of this in one part. And then the second part is space technology, where we discuss about satellites, where we discuss about ISRO, we discuss about some of the different missions, we discuss about applications of satellites. So there are all these topics that we will discuss as a part of space technology. So one part will be space science, one part is space technology. We'll start with space science and then move on to the technological aspects. So the very first thing is to understand about the universe. Now, when we say universe, and if I ask you to define what is universe, you have a broad understanding of what universe is. But when it comes to defining what is the universe, how do you define it? Without looking into what definition I have given, what is your broad understanding of the universe? Set of celestial bodies. Okay. What else? Different objects. Okay. Collection of all possible space. All right. Where all things come together. All right. Moments of all planets made of different particles, never ending from any angle. Interesting. Everything that exists, yes. It has solar systems and inner planets or gaseous planets, yes, it does have. Solar systems plus galaxies plus meteors, right? Hmm, interesting. So a lot of you have given different answers, and all of it basically sums up to what the universe is. One of the best universe definitions that you can come across is this. This was given by a scientist in the US in his book. Alexander Bolonkin is the name, and he had given this definition. Everything that exists, everything that has existed, and everything that will exist is a part of the universe. A very philosophical definition, but holds true. See, we do know that look, everything that we have is a part of the universe. There's nothing that is beyond the universe. There's nothing that is outside the universe. So that's why everything that exists is a part of the universe. But then it also adds everything that has existed in the past and everything that will exist in the future is also a part of the universe. So why are we not only saying that okay, everything that exists is the part of the universe? Why are we also accounting for the past and the future? Understand this. There is a theory, a law that is called as law of conservation of energy. What does this law say? What is the law of conservation of energy? I'm sure many of you know. What does it say? Yeah, energy can never be destroyed. Energy can neither be created nor destroyed, right? So it says that energy can neither be created nor destroyed. It can only be transformed from one form to another. All right. So this is basically what we say is law of conservation of energy. Now, how does it apply to this definition? Suppose that there is a star. There is a star that you see shining bright in your night sky. Now, the light from this star, do you think that the star just started shining and you started seeing that light? Is that the case? The answer is no. It would have taken millions of years perhaps for that light to start from the star and reach the earth. So, for example, the sun, our own sun, which is so close, the light from the sun takes approximately 8 minutes to reach the earth. So, just imagine a star that is millions to billions of kilometers away from the earth. So, it takes a lot of time for the light to come from there. So, even if let's say that star stops existing today, even if it dies today, you would realize that this, I don't know how many years from now. So that's why even though it does not exist in the future, you still see it. Similarly, a star which is not formed yet, it will be formed in the future. Something will happen, gases, bunch of gases will come together and form that star. So right now something which is just a bunch of gases and dust particles lying here and there as a nebula perhaps will form a star in the future. So something that did not exist today will exist in the future, yet it will all remain inside this universe. So that's why everything of the past, present, and the future all are part of the universe itself. So in a manner, you can say that everything is universe. There's nothing beyond the universe. Now comes the actual complexity when we look at the composition of the universe. The composition of the universe we can divide into three parts: dark energy, dark matter, and the rest. Dark energy, dark matter, and the rest. So, what is dark energy? What is dark matter? Hold on for now. I'll explain this. But before that, the rest. Let's try to understand the rest. Now, this is where the things become confusing or this complex to understand for the entire humanity. The rest, which is just 5%, dark energy is almost 77%. Sorry, dark energy is almost 68%, dark matter is almost 27%, and the rest makes up for 5%. So as you can see, 70, 25. So 70 to be exact, we say 68%. To be exact, we say 27%, and the rest is 5%. All right, the rest is just 5%. Now, in this particular scenario, when it comes to the rest, let's start with the rest. What is the rest? The rest is actually what we see. Now, in this rest, if you see, 4% of the universe, 4% of the universe is just free hydrogen and helium. Accounts for 4%, right? 4% of the universe is just free hydrogen and helium. So out of the rest, 5% also, 4% just hydrogen and helium. Coming to the last 1%, 0.5% out of it are all the stars in the universe. The billions and billions of stars that we have in the universe, they make up for 0.5% of the universe only. Then in the rest, you have 0.3% of neutrinos. 0.3% of neutrinos. Now, what are neutrinos? Neutrinos are particles which are very small. All right, these are particles which are very small and very light in weight. We say that these are chargeless and massless particles. So chargeless because they don't carry any charge, they are neutral, neither positive nor negative. And we say that they are almost massless particles also. Their mass is negligible as compared to any particle that we know of. Compared to even a proton, it's negligible. So that's why these are chargeless and almost massless particles. So neutrinos, these are chargeless and almost massless particles. Chargeless and almost massless particles. So now look at the number. In the context of what we are discussing, 0.3% is a big number, right? It's a big number. And neutrinos are 0.3% of this universe. They are 0.3% of this universe, which is a very significant number. So these are chargeless and almost massless particles. And that's why the name neutrinos was given to it. So because we have neutrons, right? Neutrons also have no charge, right? They are also neutral, but they have a significant mass, correct? They have a significant mass. So they are called as neutrons, derived from the word neutral. Now these are called as neutrinos because they were discovered by Italian scientists. So for Italians, anything that is very small, very tiny, the suffix ino will be suffixed to it. So that's why they started calling it as neutrinos. So it became neutrinos, and because of that, because of the fact that it's massless, almost massless, and it is chargeless because it doesn't carry any charge, any mass. So hence they named it as neutrinos. Now 0.3%. And then after that, we have 0.17% of antimatter and electromagnetic radiation. 0.17% of antimatter and electromagnetic radiations. Now we'll discuss about electromagnetic radiations later when we go to the chapter of IT and communication. That is where we'll have a detailed discussion on electromagnetic radiations. For now, you just know that these are radiations which have electrical and magnetic properties. So for example, our visible light, radio waves, gamma rays, X-rays, ultraviolet, infrared rays, microwaves, all these are what? All these are electromagnetic radiations. And then antimatter. Now, what do we mean by antimatter? Let's try to understand what is antimatter. Now, when it comes to antimatter, we are talking about particles with same mass but opposite charge. Same mass but opposite charge, they will be called as antimatter. So particles with same mass and opposite charge will be called as antimatter. So for example, let me ask you a question. We have electrons and protons. Can I say that these are antimatter of each other? Are they antimatter of each other? I am quickly launching a poll and not going to give you a lot of time. Do you say yes or do you say no? A for yes and B for no. Do you think that these are antimatter of each other? 42% of you think yes and 58% of you think no. The correct answer is no. They are not antimatter of each other. Why? Their masses are not equal. We had discussed this in yesterday's class as well, that protons are almost 2000 times heavier as compared to electrons. So, for something to be called as antimatter, you need to have same mass but opposite charge. So, here you have electrons and positrons. Now, positrons are very unstable particles, but this is where the charges are opposite and mass is the same. 9.1 into 10 to the power of minus 31 kg is the mass that you have for both electrons and positrons. All right, so that's why they have same mass but opposite charge. So that's why electrons and positrons, they can be called as antimatter. All right, they can be called as antimatter, but electrons and protons cannot be called as antimatter because protons are almost 2000 times heavier as compared to electrons. So just understand the concept of antimatter, because usually you'll come across an antiparticle or an antimatter which is very highly unstable. Same is the case with positrons as well. They're very highly unstable. So they do not really exist in nature as easily as electrons, protons, neutrons, etc. do. Then lastly, we have heavy elements. What do we mean by heavy elements? And as you can see, heavy elements make up for 0.03%, right? 0.03%. Now, heavy elements, basically, these are all the elements apart from hydrogen and helium. All the elements apart from hydrogen and helium, they are called as heavy elements. So in this context, otherwise in chemistry's concept, when we talk about heavy elements, we mean something that has very high atomic number, right? Any element with very high atomic number could be called as heavy element. But in this particular scenario, when we are talking about astrophysics, when we are talking about space technology, apart from hydrogen and helium, which already has been accounted for, right? Already has been accounted for 4% of the universe. All the other elements, they are called as heavy elements. Now, as you can just imagine, that everything around you, everything that you see, everything that you observe, they are made of heavy elements, correct? Carbon, oxygen, nitrogen, chlorine, bromine, iodine, uranium, thorium, plutonium, whatever we discussed. All these are what? All these are heavy elements. So everything around us, everything that we are seeing is made of some kind of heavy element or the other. So it's unimaginable that it makes up just 0.03% of this entire universe. Now this is where comes the concept of dark energy and dark matter. Dark energy, that makes up 68% of the universe, and dark matter, that makes up 27% of the universe. So let's try to understand what do we mean by dark energy and what do we mean by dark matter. Now in this particular scenario, when it comes to dark energy, before we try to understand what we mean by dark energy, also let's try to go a bit into the history of our understanding of the universe. Today we understand, we have a better understanding of the shape of the universe. All right, today we have a better understanding of the shape of the universe. But in the past, there is something called as the steady state theory, which used to say that the universe, the shape of the universe that we have today, the structure of the universe that we have today, is the same as it was millions of years back, and is going to be the same millions of years from now also. The relative positions will remain the same. So let's say we have three galaxies. You have galaxy A, we have galaxy B, and galaxy C. Right? We have these three galaxies, galaxies A, B, and C. So what our understanding was that this is always going to stay like this. They'll always remain in a steady state. So this galaxy A, B, and C will always remain like this. There will be no change in their relative positions. There will be no change in the structure of the universe. So this is what the basic understanding was. And you can say that all the scientists, they believed this to be true. Then came a scientist, as I told you, that we will keep taking this scientist's name in every chapter. And this was Albert Einstein. And when Albert Einstein gave his theory of relativity, that is, theory of general relativity and theory of special relativity, this is where he found, through his mathematics, through his equations, they were suggesting that the universe should be expanding according to those equations that he had derived, that the universe should be expanding. Now, even he was a very firm believer of the steady state theory, and that's why he thought that he was wrong. Albert Einstein thought that he was wrong. Forget about a person like me or you. So, even he thought that he was wrong. He did not have the confidence in his equations. He thought that he committed some kind of mistake. The universe is static, universe should remain static. There's no possibility that universe can expand. But his equations were suggesting that universe is expanding. So he changed his equations. It's like when you know the answer, right? Many a times it might have happened in your childhood that you already know the answer, but you do not know the steps how to reach that answer. So you make up the steps in a manner that you reach the answer because you already know the answer. So something similar happened here, that he already believed that universe is in a steady state. So that's why his equations must be wrong. So he corrected his equations. He changed his equations. He added something which is called as a cosmological constant to his equations so that he can make the universe steady again. So he did that. Almost 12 years later came another scientist, Edwin Hubble. You might have heard this name also. Edwin Hubble. Now, Edwin Hubble, with his independent studies, he also suggested that the universe is expanding. His studies also suggested that the universe is expanding. Now, Albert Einstein also read the paper and he saw what the paper was and he thought that yes, this is correct. What Edwin Hubble is saying is perfectly correct. And Albert Einstein, very famously, it is said that he said that this is the biggest blunder of my life. This is called as Einstein's biggest blunder. Even if you go to YouTube or you just search on the internet, you'll find that there are documentaries made on it. Einstein's biggest blunder. Because some believe that Einstein famously said that this is the biggest blunder of my life. Because I had proved this almost 12 years back, but just because I did not have firm belief in whatever I had written or what my studies were suggesting, I did not go forward with it. So such is life, that Edwin Hubble got uh, the theory correct, and he was the one, then that's why, who suggested that the universe is expanding. So until now, our beliefs, now they have been quashed, that the universe is not in a steady state, the universe is expanding. Not only that, later on we found that it's not only that universe is expanding, but the universe is expanding in an accelerated manner. Accelerated manner, what do we mean? A normal expansion, a normal expansion would be like this, that it is expanding. But when we say that it is expanding in an accelerated manner, it is like this, the expansion like this. So this is normal expansion. I know this is not important for you, just to give you context, I'm making these figures. And this is accelerated expansion. Because otherwise you'll keep searching for these theories and explanations, and it's very difficult to find them. So this is where we understood that this is how uh, later on we found that universe is expanding in an accelerated manner like this. As you can see, universe is expanding in an accelerated manner. This is accelerating expansion. So that's why the relative positions, if you see, the relative positions also are changing, because the universe is expanding and the expansion is happening everywhere. It's not that the expansion is happening only at the edge of the universe. The expansion is happening everywhere. So the galaxies are also moving apart. The galaxies are also moving away from each other because there is expansion everywhere in the universe. It's just like inflating a balloon. That if, let's say, you have 2 points on the balloon, as you start inflating it, the distance between these 2 points on the balloon will start to increase. So something similar is happening. Accelerated expansion of the universe. Now, for any kind of movement to happen or these kind of expansion to happen, there must be some kind of energy behind it, right? There must be some energy that is causing this accelerated expansion. What is that energy? Nobody knows. Why do we call dark energy as dark energy? The reason is not because there are some dark forces and there is some kind of evil dark energy behind it. No. Dark energy is called as dark energy because we do not know what kind of energy it is. We are in the darkness. We are in the darkness. We do not know what kind of energy it is. Hence, we named it as dark energy. That's why we are calling it as dark energy, because we do not know what form of energy it is. We are just saying that, look, if the expansion is happening, there must be some kind of energy that is pushing this expansion. But what kind of energy it is, we do not know. We have no clue. We have no idea. So that's why we named it as dark energy. That's why it was called as dark energy. So that's why if you look at the definition, dark energy is the unknown form of energy. Unknown form of energy which is hypothesized to permeate all of space, tending to accelerate the expansion of the universe. So it is dark energy which is behind the accelerated expansion of the universe. All right. This is the one, this is which is leading to the accelerated expansion of the universe. So this is what dark energy is. We haven't been able to yet find or understand what dark energy is. We do just understand that, look, there must be some form of energy that is leading to the accelerated expansion of the universe. So let's call it as dark energy until the time that we find what kind of energy it is. Until then, it will be called as dark energy. Interestingly, it makes up almost 70% of the universe. Almost 70% of the universe. Then there's the other concept called as dark matter. Now, what do we mean by dark matter? Now, when it comes to dark matter, it is a mysterious, non-luminous substance making up vast majority of matter in the universe. What do we mean? What scientists believe is that there is a lot of unexplored matter which remains unexplored, unknown to us, because we do not have the correct instruments to find it. We do not have the correct instruments to see it, and that's why it remains unknown to us. And it must be making up almost, when we say majority of the matter, out of all the matter that exists, probably 80% of that matter is dark matter. 80% of all the matter that exists is dark matter, and making up 27% of the universe. Now, in this context, do we know what kind of matter it is? We absolutely don't. But then how do we know that it exists? How do we know that there is something called as dark matter? Where is this dark matter? The answer is probably everywhere in the universe. Can we see them? No, we can't. Do we have the right instruments to see them? No, we don't. But then how do we know that they exist? You can say that these are based on simple calculations. Suppose that you are sitting right now in your room, right? And in your room, you are there in your room, maybe a table, chair, your device on which you are watching the lecture, maybe some books, maybe some notes, maybe your clothes, right? So there could be a lot of things. Then there are walls in this room. So let's say I tell you that, okay, uh, tell me the entire weight of this room. So you pick up one by one, you pick up everything and you weigh them. And let's say everything combined comes out to be 1000 kilograms. All right. You have taken everything one by one and you have measured the weight, and you say that, okay, it is 1000 kg. But then you pick up the entire room as a whole and you see that it is not 1000 kg, but 5,000 kg. Now, how do you explain that? How do you explain that it is not 1,000 kg but 5,000 kg? Because you have already accounted for everything that you saw, everything that you could see around. So there must be something that is unaccounted for, right? There must be others in the lecture, others in your room who are attending the lecture. Probably they are finding these lectures interesting, and that's why they're attending along with you, just that you don't recognize. Sometimes just that there is passing wind, or some shut doors or windows that make you recognize that there is somebody else in the room. So if that was the case, maybe the extra weight is coming from there. Maybe there are 10 more people in the room, and I have no intention to uh, create sleepless nights for you. But this ghost of the universe is what we call as dark matter. The matter that exists, the matter that exists, but we have never seen it. Our instruments have never seen it, but they do exist. Our calculations show that they exist, but we haven't been able to see them. We haven't been able to observe them. So that's why this non luminous, mysterious matter of the universe is dark matter. And why are we saying that it is matter? How do we define matter? Anything that has mass and occupies space is called as matter, right? This is how we say that something is called as matter. Anything that has mass and occupies space is called as matter, right? So similarly, dark matter also must exist, because otherwise we do not know how the weight of the universe is so much, how the mass of the universe is so much. So there must be some matter, and that's why we have named it as dark matter. Because why? Because we don't know what kind of matter it is. We just know that it must exist. That's why it has been named as dark matter. Now, there is this mission which has been in the news since last year, and this is the Euclid mission. And this Euclid mission is a basically to explore mission to explore the dark universe. Now, when it says to explore the dark universe, it basically means dark energy and dark matter. Dark energy and dark matter. All right. So that's why what we see is that when it comes to dark energy and dark matter, we see that this is a mission that has been taken for the first time to explore the dark universe, to explore dark energy and dark matter. So the name is Euclid mission, and this is exactly what it's supposed to do. That it is supposed to take. So as you can see, this was in the news in November. Europe's Euclid telescope captures unprecedented views of the deep space. So these kind of images were published by the Euclid mission. That this is something where we are trying to explore the dark universe so that we can get some idea about what is dark energy and dark matter. Otherwise, when it comes to dark matter, right now we do not know what it is. Right? Height, weight, last seen, everything is not known. The search cost in billions, right? Billions of dollars have been used up in trying to understand what is dark energy and what is dark matter, yet we do not really have an idea until now. So this is where we are with the exploration of dark energy and dark matter. So any questions if you have from whatever we have discussed until now? If we fill the room completely with a known matter, still this variation will be there. Yes, it will be there, and it's not about the room. Room was just an example, but we are talking about filling up the entire universe. So hypothetically, if you say that okay, I can fill up the entire universe with matter, that would also mean that a lot of gravity will be created, because matter has mass. Wherever you have mass, there you have gravity. So then gravity will be created, and then it will completely change the structure of the universe. So that's why filling up the entire space is not even possible for us. Really, network is going low when you teach dark matter. I hope there is nothing extraordinary in your room. What is beyond universe? Until now, whatever scientific studies have been conducted, they explain that there is nothing beyond the universe, that there is nothing beyond the observable universe, and there is no celestial body, there is nothing, no matter that we see in the universe beyond this universe. Please explain one more time dark matter. See, dark matter, simply what we are saying is that dark matter is that unknown matter which which we are able to calculate, that our calculations show that, but we have never been able to observe them. So unobserved matter that must exist but we have never seen it is called as dark matter. What is the exact difference between dark energy and dark matter? There is no similarity between the two. Dark energy is related to the accelerated expansion of the universe, the energy behind the expansion of the universe. And dark matter is just a form of matter which is unknown to us. Can we say this dark mass is converted in energy? Uh, I wouldn't say that. But what was the thought process behind you asking this question? If you can repeat, I can tell you something about it. So curious to know this. Are all paranormal energies included in dark energy or mass? Uh, See, first thing is whether there is anything paranormal or not, that has to be debated. Many do not believe that there is anything paranormal. Many believe that there is something paranormal. So this goes beyond our discussion. So James Webb Space Telescope is related to Euclid mission? No, they are completely different. James Webb Space Telescope is an infrared telescope, which which is not related to the observation of dark energy or dark matter. So you have told that it is dark matter because it has mass. How did scientists measure that mass? So basically, it's about, let's say, when they are observing any given galaxy. So let's say when they are observing a galaxy, they observe the movements, they observe the forces. So the forces tell a story, the movements tell a story, and that's why they understand from there that when you calculate the movements, the trajectories that you see, the forces that you observe, they are not coinciding with everything that they see. So there must be something else also which is leading to those motions or leading to those forces. So that is where the calculations come from. Is multi-universe theory true? Until now, there is no scientific evidence or proof to prove it to be true beyond the movies, of course. My room's dark matter is liking your video too. It's time for you to perform some exorcism, maybe. Can we say that matter is converted into energy? Can't really say that. How these percentages are obtained? 68% of dark energy. This is basically on the basis of the observations and the calculations that we do, and there are a lot of steps that are involved in doing these calculations. Cosmic microwave background we'll discuss in some time. Relativity theory of Einstein, can we say that dark matter is converted into energy? No, 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 no. That basically we can't say, because we are not saying that that matter is not existing or it is converting into something else. We're just saying that it exists, just that it's unknown to us. So, I mean, if there will be still variation while calculating the mass, if the area we calculate is completely occupied by known matter. See, as you occupy the area with known matter, of course, what will happen is that it leads to the expansion of that area itself. So basically, what happens is that the space itself starts to uh, uh, expand. So, for example, let's say take this as an example. Let's suppose that you have a balloon which is filled with air, and then you say that no, I don't want to let any air be there, so I start filling water in it. So what happens? You will be able to fill water, but as you fill water, it if let's say the air does not go out of the balloon, what happens? The balloon will start to expand. If that's not the case, the air goes out and water replaces it. So in this particular scenario, what might happen is that if let's say you have closed the balloon and you are not letting the air go out, what happens? It would first start to expand. The balloon itself will expand. So similarly here, if you let's say try to occupy the entire space with matter, that you want to fill up the entire space with matter, the space itself starts to swell. It starts to expand. This is where the things will go. Is hell or heaven also found in universe? I'm not the one to answer this. Hmm. So Lagrange point we'll discuss. I mean, not today, probably tomorrow or day after we'll discuss. Does dark energy, dark matter have any connection with black hole? No. It's an independent topic when it comes to black holes. We'll discuss that. So now let's come to the formation of the universe. Now, formation of the universe, there are various different theories. We have the Big Bang theory, we have steady state theory, we have eternal inflation theory, oscillating universe theory, string theory, and the Big Bounce theory. Now, out of all these theories that we have, the Big Bang theory is the most widely accepted theory, right? It's the most widely accepted theory. And apart from that, if there is any other theory that is often in the news, it is the string theory. So that's why these are the two theories that we are going to discuss in detail. Others we are going to skip because there is no scientific evidence that has been able to prove the other theories. All right. So that's why we'll not be bothered by other theories. So for example, steady state theory, we already discussed that it has been discarded. Eternal inflation theory, it talks about the concept of multiverse. Talks about the concept of multiverse, again a concept which does not really have a lot of sound scientific backing. Then oscillating universe theory. Oscillating universe theory says that the universe is right now expanding, but then it will contract, again it will expand, again it will contract, and this is how it goes. And the big bounce theory also says something similar, that there are contractions and expansions. In the universe. So again, what we do not really have a lot of scientific evidence that can substantiate these theories. So that's why Big Bang theory is the most widely accepted theory. And then there are some who also talk about string theory. So let's try to understand these. The first one is the Big Bang theory. Now, what does the Big Bang theory say? The Big Bang theory says that the universe was very hot and concentrated in the distant past, and ever since then it has been stretching and cooling. The entire universe would have been very small in size when the universe was born. It would have been smaller than even a proton, and it was like a soup. The entire universe would have been like a soup, just like how you have different ingredients which are mixed in the soup. Similarly, the entire universe would have been like a soup, and all the different types of matter, different types of forces, energies, all they were mixed like the ingredients which are mixed in the soup. So this is what the Big Bang theory says, that the universe was very hot and concentrated in the distant past, and ever since then the space has been stretching and cooling. So what it says is that universe was smaller than a proton, and all the matter, all the matter, forces, energy, etc., were like a soup in this small particle. All right. And also, when we say that it was very hot and concentrated, the temperature would have been, as it is estimated by the scientists, the temperature would have been of the order of 10 to the power of 31 degrees Celsius. 10 to the power of 31 degrees Celsius would have been the temperature of this universe. So that's why very hot and concentrated in the distant past, and ever since then it has been stretching and cooling. Now, when it comes to the Big Bang Theory, the Big Bang Theory today has become the most widely accepted theory about the universe. Why exactly is that the case? There are three very, very important evidences that support the Big Bang. The very first evidence is something called as Big Bang nucleosynthesis. Big Bang nucleosynthesis. Now it sounds very complex, but reality it's not. Big Bang nucleosynthesis is nothing but the abundance of hydrogen and helium. Now what we discussed is that out of the 5% of known universe, 4% is just hydrogen and helium, meaning that 80% of what we know is just hydrogen and helium. So that's why this has been basic. This is what Big Bang nucleosynthesis is, nothing but related to the abundance of hydrogen and helium. Then the second evidence is what we call as Hubble expansion. Hubble expansion. Now again, what do we mean by Hubble expansion? Again, something that we have discussed. Hubble expansion is the accelerated expansion of the universe. Accelerated expansion of the universe. And then lastly, the third evidence is a very, very important evidence, and also from examination perspective, this becomes the most important thing. And that's why when you look at uh, these figures that you see, these pictures that you see on your screen, it is related to something called as cosmic microwave background. This is related to something called as cosmic microwave background. All right, cosmic microwave background. Now what do we mean by cosmic microwave background? Now here you have three terms. The first term is cosmic. What is cosmic? What do you mean by cosmic? When do you say that something is cosmic? Okay, in the cosmos. What is cosmic? Yeah, correct. Related to space, related to universe, correct. So cosmic is anything that we have in space. Anything related to the universe can be called as cosmic. So for example, all the celestial bodies are also called as cosmic bodies. So that's why when we say cosmic, you can say in a manner it is nothing but space related. Then the second term is microwave. What is microwave? Microwave basically is a kind of it is a kind of electromagnetic radiation which is related to heat. Wherever you have heat, wherever you have very strong heat, you have microwave there. So for example, you might have used microwave ovens for cooking the food or or heating the food. So these microwave ovens, they run on microwaves, right? They run on microwaves. So microwave is what? Microwave, these are electromagnetic waves related to heat. So, when we say cosmic microwave background, what we mean is that there are microwaves that we can observe in the background, and that's why these have been named as cosmic microwave background. Now, what kind of background? Now, if you look at these three figures, pictures have come from three different uh, space missions that have been taken by NASA and also associated with European Space Agency. The very first one was COBE, and this was back in 1993, which gave the first evidence or the first picture of the cosmic microwave background and also won a Nobel Prize for doing it. Then the second one was WMAP. This was 2006, and as you can see that this is a much clearer picture, right? Much clearer picture compared to what we had with COBE. So WMAP also got a Nobel Prize. And then third one, as you can see, Planck is a way better picture. This was taken in 2009. So these have shown evidences of cosmic microwave background. Now, if you look at this picture from the perspective of WMAP, as you can see that we are looking at the outer universe, and as we are looking at into the outer space with the help of WMAP, we see all these celestial bodies in the path. But if you look into the background, what do you see? You see microwaves there, right? This this basically is the cosmic microwave background. This is the cosmic microwave background. So that's why cosmic microwave background, because we are seeing this in the background, that there are all these celestial bodies, and in the background of these celestial bodies we see microwaves, right? So this is basically what cosmic microwave backgrounds are. And why are they important? Why are we saying that they are evidences supporting the Big Bang theory? Because what we are seeing is that the universe was very hot and concentrated in the distant past, and ever since then it has been stretching and cooling. So when the expansion started in the universe, it would have been very hot. It would have been very, very hot, and that's why microwaves would have been released there. And this is precisely what we see here. So that's why cosmic microwave background. So these microwaves would have been generated when the universe expanded at the time of Big Bang. Microwaves would have been generated when the universe expanded at the time of Big Bang, and these microwaves are observed with the help of special instruments like COBE, WMAP, etc., and are called as cosmic microwave background. So this is what the concept of cosmic microwave background is. Now let's stop here. We'll discuss about string theory in tomorrow's class. So if you have any questions from whatever we have discussed in the last half an hour or so, please let me know. At some places, Doppler effect or redshift and blue shift are also given as evidences of Big Bang theory. See, when it comes to redshift or blue shift, it does give us some evidences about expansion of the universe also. But at the same time, when it comes to Big Bang, uh, strictly speaking, I would never say that blue shift or red shift is an example of Big Bang, or it's an evidence supporting Big Bang. Because Big Bang basically talks about when the universe was just a particle and the first expansion that started. red shift and blue shift, they are examples of expansions that are happening today, not what happened in the distant past. So I wouldn't 100% agree that red shift or blue shift are also evidences of Big Bang. Previous slide. Previous slide. Do aliens exist? For this, you will have to come to my podcast. This is not the correct place to discuss this. But why not? They must exist. It's very, very unlikely that we are the only ones in this entire huge universe who are existing. Big Bang Theory was introduced by Stephen Hawking, or was it already existing? No, it was existing before that. In the 1960s itself, it was suggested. Why Planck did not get the Nobel Prize? It's not about that, because the first two had done extensive jobs and Planck was an extension on it. Module 1 PPT is not available. I'll again check with the team. I'm not sure what the problem is, if there is. Hmm. Any further questions? About the annotated PPTs, again, I'll ask the team. I'm not sure because I had informed them that this is a complaint coming from the class. I'll just check with them once again after the class. We got the body of aliens, I don't know, seen in the newspaper. See, there have been many reports like this, and there are a lot of conspiracy theories here and there. Can't say anything. WMAP full form. WMAP full form is Wilkinson microwave anisotropy probe. So that was the name that was given to it. Right. So let's pause our classes here, and we'll again meet back tomorrow. We'll start with string theory first, and then we'll continue with space technology in tomorrow's class. Thank you.
Because I haven't done yet.